So with that in mind, let's go ahead and start developing the constant acceleration equations. Let me list them over here. There are going to be 5 of them. As we'll find, the fact that there are 5 of them and the fact that I have 5 variables I've chosen as my winners is not a coincidence. So let's go ahead and take what we already know and just start shoring up the relationships. One of the things, of course, we know, the definition of acceleration. We defined average acceleration. Acceleration is how much your velocity changes with time. That was the way we wrote it down before. And we also, just to remind you, if we have constant acceleration, then that will yield you not just your acceleration on average, not some amalgam of how much you procrastinated in changing your velocity at first and made up for it later, but it will literally give you at every moment what the instructions were to the velocity on how to change. If you have constant acceleration, then how the velocity evolves with time is a fixed amount. So all I'm going to do with this equation is rearrange it, and it's going to be my equation number 1. All right. So first of all, I want to do my notational change here. So I'm going to drop the hats, put in an x subscripts instead, drop the delta on the t. And then for reasons that are just bordering on practicality, what I have at the current moment is v final minus v initial over t divided by by t equals a. That would be perfectly fine, but for practical purposes, it's solved for v final. So that's equation number 1. So we're basically just taking what we already talked about and just kind of reformatting it. Equation number 1 is really just a rearrangement of the definition of acceleration. All right? Let's keep going. Let's grab the things we already know and just get them into a format which we will find is incredibly useful for problem solving. Here's another equation we talked about. The definition of average velocity, going back even further. So the definition of average velocity is the displacement you have divided by the time you took to do it. So let's do the same notational change. We'll knock off the vector hats and put in the subscripts. We're not going to put a subscript on delta x because it's already got an x there. And you could solve this, and you get this equation. Oh, and I also want to knock off the delta off the t, just for time savings, for having to write that. There's only one problem with this equation. I'm not going to include it on the list just like this. What's the issue with this equation? Anybody, can anyone see it? What's that? Oh, this is my list. What's wrong? Average velocity is not, that was a loser, right? I picked 5 winners, and the average velocity I did not want to do. So what if I then substituted in for average velocity, and I could somehow get the average velocity using the 5 that I said I would be concerned with? Well, you can actually do that. Here's the beauty of constant acceleration. The beauty of constant acceleration is smooth velocity changes. So if you have constant acceleration, you're trying to get from one initial velocity to another final velocity, you're going to just smoothly connect them. You're not going to dilly-dally near v initial. You're not going to dilly-dally near v final. You're just going to smoothly connect them. What do you think? How do you think I could get the average velocity from the initial and final? Any ideas? if I have, say on a number line, I have v initial here, and I have v final here, where do you think that v ab is going to fall on, relative to the midpoint? If you don't procrastinate near this, you just smoothly connect them. How can you get v ab? Where's v ab? It's halfway. So because you have constant acceleration, the average velocity is just the halfway point between the initial and final. That does not always work, okay? That works because we have constant acceleration. There's lots of different ways to connect one initial velocity to another final velocity. You could spend most of the time near v initial, and the average would be thrown heavily towards v initial. You could spend a lot of time near v final. You could spend most of your time near v final, and the average would be thrown heavily towards that. But that would be herky-jerky changes. We are smoothly connecting them. That's what constant acceleration means. It means smooth velocity changes. Okay? So with that in mind, I can get rid of v ab and put in this, and I'm going to have another equation. And for reasons that don't really matter, that's traditionally listed as the fourth one. Now you can see it's expressed in terms of all of the variables that I chose to use. Remember, if it's helpful to you, that the quantity in parentheses there is just v ab. Okay? Okay. So that's 2 of the 5. And as I tell you how to get the other 3, I'm going to have to give away why are there 5 of these while there are also 5 of these. Well, the whole goal of having 5 equations is that I want to have every one of the 5 variables take a breather, which is to say I want to let each one of them take a turn sitting out. So I'm going to add a column over here, which one each of these equations is missing. You can look at the ones we already have and notice the pattern. Out of the 5 variables, which one is this one missing? Displacement. It relates to the other 4, but displacement is taking a breather. What about this one? Which one is this one missing? Acceleration, while the other 4 interrelate. Well, this gives me a strong clue how I'm going to get the other ones. I just have to algebraically ram them all together, letting each one take a breather. For example, let's say I wanted to let v final take a breather. If I want to take v final and let it take a breather, how might I get that? Well, I'll take this equation, which is v final equals blah blah blah. I'll plug it in here for v final. And then I'll get an equation where v final's gone, right? Because I substituted one for the other, right? Let me tell you what you get. You can try it yourself. But this is what you get. Delta x equals v initial times t plus 1/2 a t squared. By the way, this set of equations is prominently on your equation sheet. You don't need to memorize it. You just need to know how to use it. All right, let's let time take a breather. Now you're spoiled for choice how to make this. But basically you have to take 2 of these and ram them in together so that you can get rid of time. Now this is a hornet's nest because it's got t and a t squared. As we'll find, quadratic equation is occasionally necessary to solve for t there, so let's not do that. Let's use 1 and 4 again. For instance, we could solve equation 1 for t and then put it into equation 4 in for t, and we get a new equation without t, right? So let me tell you what you would get. Try it if you want yourself. I'm just telling you what the algebra results in. You get v final squared equals v initial squared plus 2a delta x. Okay, and finally, which variable hasn't taken a turn yet with a breather? The initial. So that's our 5th and final equation. there are no more because there are no more variables left to take a turn sitting out. So that equation, pick your favorite two. They're multiplying, so you have options, right? You have now 4 equations to choose from. Pick your favorite one. Solve for v initial, put it into another one so that v initial will be gone. And this is what you'll get. Something very similar looking at equation number 2. Except v initial is replaced by v final, and there's a minus in the middle of the right-hand side instead of a plus. So there are your 5 equations, and these are going to be your friends because they can attack a huge number of problems. As long as it's a constant acceleration problem, this is your toolkit. And the reason why we've done all of these algebraic collisions now is we've done them once symbolically so we never have to do it again. If you find yourself attacking these problems and using 2 of these equations, it's not that you're doing something wrong, you're just working harder and not smarter. Because whatever those 2 equations you're using, they've already been rammed together here into one package, and you should be using that one instead. Okay? So let's talk about the problem-solving strategy associated with these 5 equations. So the problem-solving strategy, kind of think of it as going along with these equations. So in order to solve a constant acceleration problem, you need to be given 3 of the 5 variables. So remember there are 5. We need to be given a minimum of 3. I'll usually mark those with a check mark. Check mark means I know it. I'm going to use it. Usually you're asked for a 4th variable. I usually label that with a question mark because that's what you're trying to find. It's really important here to bookkeep all this alphabet soup. In math class, everything is, a number except x. But here we have a bunch of things flying around, and you want to keep track of things that you know and things that you don't know. There will also be a 5th variable that you don't know and don't care. Usually I'll mark that as a cross-off. It's not an x. I know in math you usually solve for x, but that's like I don't know it, I wasn't given it, nor do I care because it wasn't asked for. So it's neither here nor there. You still need to acknowledge the fact that it's part of this problem-solving strategy. Now that makes it seem more abstract, so let me just give you an example. What you do is you say list the 5 variables in no particular order, and then start bookkeeping. So let's say, for instance, I was given delta x, v initial, and v final. I was asked for acceleration, and I don't care about the time. So if I don't know and don't care about the time, let's use the equation that doesn't even have time in it. Right? So this would tell me that I want to use equation number 3. So perhaps, strangely, it's the thing that is not mentioned that tells you what to do. So if you don't find that t is given nor asked for, then you want to make sure you avoid anything that has to do with it. So what do? You take equation number 3. Equation number 3 has 4 variables in it. What are those 4? 3 that you know, 1 you don't. You just solve for it. You're good to go, right? Does that make sense? And, of course, because we have all 5 of these, no matter what, you will be able to have an equation to choose from. Whichever variable is omitted, you pick the equation that has that's missing that one, and that's the one you use. Now you might ask, well, what if you're given 4 things? What if you're given 4 things and you ask for a 5th? Well, then you're spoiled for choice, right? Then varieties of these would work. You're 1 and done. Use 1 equation, you're done. But this strategy gives you the minimum amount. The minimum amount is 3. And with a single equation, you will be able to get your answer because you use the equation that doesn't have the thing that is missing. So there's no manipulation required. All the manipulation has already been done over here. Okay? So the next order of business is then to take our toolkit out for a spin, right? Let's try it on an example problem, the kind that your homework number 2 is going to be chock full of. Before I do that, are there any questions? All right, let's set it up. This is going to be my example number 1. The first, but not the last. Here's how the problem goes. A car is initially 8 meters from a stoplight, traveling at 5 meters per second when the light turns red. If the car decelerates at 2.5 meters per second squared, A, how far from the light does it stop? And B, what is the time to stop? So this is a very nuts and boltsy kind of entry-level type of problem. I'm going to use the opportunity to do a couple asides during this problem to show you important problem-solving strategies and shortcuts and things like that. But this is, aside from just using the opportunity to discuss a few things, because I feel like this is really the first proper example of the class, I'll do a couple side points as well. First thing with problem-solving strategy, can't emphasize this enough, always draw a picture. Okay? It's fun to draw a picture, and if you just try to skip over it, trust me, oftentimes you miss a detail. Physics is very detail-y, so you have to think in terms of small incremental steps, so it doesn't ever seem like you're just trying to jump straight to the answer. Trust me, the problems get hard enough, you can't just jump to the answer. You have to be methodical. And one of those things that you have to do to be methodical is draw a picture. Get started off right. It's fun. You don't have to be too crazy artistic. I'm not a great drawer. But just enough to get the details. So I was given that it's 8 meters from the light to start with, and I've chosen arbitrarily to draw it in this orientation. Notice the problem does not hand me what the positive axis is. I just am going to decide that. I'm going to decide that the car is coming in from the right. And so for me, the initial velocity is plus 5 meters per second, right? So it's plus because I decided that it's in my plus direction. What's the direction of the acceleration? Is it to the right or left? Left. I want to slow down, right? So we learned last time that the velocity and the acceleration have to point opposite for you to slow down. And in my case, what that means is that the acceleration is plus or minus. Minus. Okay? Minus 2.5 meters per second squared. The problem did not hand me that minus sign. The diagram is where you pick that up, right? You put it in. The problem just told me it decelerates. It's up to you to know that that means that the velocity and acceleration are opposite. So whichever one you give a plus to, the other one has to be given a minus. You have to put that in. All right? That's pretty much the paragraph turned into a picture. Much easier to synthesize that way. Let's go ahead and tack part A. So part A, I'm going to put down the variables in no particular order. At this point, I notate them differently, but do remember that all of them, with the exception of time, can be plus or minus. So let me put in what I know. I know my initial velocity is plus 5 meters per second. I fill it in. That's known. I know my acceleration is minus 2.5 meters per second squared. What's my final velocity? 0. I want to stop. 0 meters per second. So there we go. There's my three things. 1, 2, 3. That's the minimum number. All right. Which thing do you think I might want to look for in part A? I might want to find the displacement to help me out, right? How far? It's a meters question. I don't care about the time. At least not until part B. So I don't need it yet. So in part A, time, don't know, don't care. That leads me to which equation I want to use. Which one? The 3, right? I want to pick the equation missing time. So equation number 3. All right, let's write it down. Go a little bit slowly at first. We'll write down the equation first, so I want you to know what equation I used. In this case, the thing I want is not isolated, so I algebraically solve for it. So I solve and I get the displacement. Looks like this. If you can't do the algebra that fast, then at some point hopefully you will be. Otherwise, it's just time spent on exams that you could be doing something else. If you're not accustomed to solving algebra symbolically, that's one of the things that the workshops and the Learning Center will be helping you with. That was not physics, that was just math. So, I'm poised to find my answer. So, let me go ahead and just put everything in. 0 meters per second gets squared minus 5 meters per second. And then I put in everything. And whatever that crunches down to is my answer. So let's find what we get here. First of all, I guess let me do this step by step here once so I never have to do it again. I get 0 meters squared over second squared. Remember that the powers apply to the units as well. Minus 25 meters squared per second squared. Denominator, I have negative 5. Okay, so the numerator, it is nice to see that the two things being subtracted have the same units. Okay? Now I know that one of them is 0, so it's kind of silly to write it there, but I did want to make a point that if you ever wind up trying to add or subtract two things that have different units, that makes no sense at all. I think that's one of the questions on your homework number 1. You can add a meter to a meter. You can add a meter, or you can add a second to a second. You can't add a meter to a second. That makes no sense. So if two things are going to be added and subtracted, they have to have like units. Luckily, that is the case, right? So same units. At this point, let me just ignore that because it's a 0. So I just get negative 25, right? Also, I can work on the units part. Actually, let me cancel first. Let me do it in red so you can see. So first of all, a negative and a negative. That's positive. I can cancel. These are both cancelable. If you need to work it out more carefully than that, you can. I get a meter squared and a meters, so that cancels. And so the only units remaining are meters. Is that okay? Yeah, I'm trying to find a displacement. If I wind up with seconds, that's a weird displacement, isn't it? That doesn't make any sense. Okay, so I did this once, so I never have to do it again. Okay, so let me talk about how I treat units in this class. Now, this is not good. I put this class because some of your other instructors may be annoying and they want you to drag around your units, so who knows when, and prove that the units for something that you already know what it's going to come out to be in is this, okay? I don't need you to reinvent the wheel and prove to me that displacement comes out to be meters, okay? It's just a waste of time to me. We have other things we have other fish to fry. So here is what my approach to units will be in this class. Okay? Step 1. Get your sniffer out. Look around in the problem. Look if there's anything that's not SI. If it is not SI, get it into SI. So all into SI at first. Then I'm perfectly fine with you dropping the units in your entire calculation. So that means you don't need to drag them around through your whole calculation, which, by the way, you should be solving the algebra symbolically anyway, so there should be nothing plugged in yet. But even when you get to this stage, don't bother putting in all this stuff, okay? Just get the number, and then add the unit onto the answer. SI unit, of course. A lot of time savings there. Maybe all your instructors might not let you get away with that. So here what we would have gotten is just 25 over 5 plus 5. And then what you've done is to say, oh, it's a displacement. Hey, I don't need to reinvent the wheel. Displacements come out to be in meters. So you will never see me plug in the units again. Now, a word of caution. Everybody likes step 2. You don't have to drag around the units. But steps 1 and 3 are not to be taken lightly. The SI unit system is self-bookkeeping. Everything will work out perfectly like this, but you need to make sure you're in that unit system, which means you have to develop a real nose for things that are not SI and fix it to start with. And step 3, you need an encyclopedic knowledge of what are the units of things in SI. It's easy here with displacement. You can remember it's meters. We'll introduce so many more units, and you need to know what are the units of force, what are the units of momentum, what are the units of energy, so that you can actually tack them on. So again, as I mentioned before, there's a units guide that's posted for you. I would have it as a reference throughout the course, just like you have your exam equation sheets as references, so that you can look and always see what are the units of things to tack on. And hopefully at some point you don't need to refer to that anymore, you just know. Okay? So, that's a word about units. Never going to see me do this unit cancellation again, because we're going to assume that the SI self-bookkeeping just handles everything. That's the beauty of SI. It takes care of all the units for you, as long as you're on that common platform. Have any questions about units before I get back to the problem? Okay. So, I have my displacement as 5 meters. So what do I put into the box in WebAssign? How far from the light do you stop?
3.
What? 3 meters. Watch out for that kind of thing. Displacement was not the final end-all be-all, okay? It was close, but remember that this means I went 5 meters to the right during my braking, but you were 8 meters from the beginning, so if your displacement is 5 meters to the right, what was being asked for is how much you stopped short. Okay? So be aware, read the question carefully. Maybe it's a little bit more complicated than just find me one of the 5 variables and throw it in there. Another thing that I might mention at the same point, you will find oftentimes that the WebAssign problem is not going to be a tyrant about what it says is plus and what is negative. That is entirely up to you. That is the scaffolding that you choose to put on the problem. If I had chosen positive to go that way, and therefore chosen this to be negative and this to be positive, there's nothing wrong with that. It's in the eye of the beholder. There's no universal positive axis running through Wichita, Kansas, okay? So WebAssign is always going to ask you the answer in a neutral way. How far is a distance? No sign. It's going to ask you things like how far, how fast. How fast implying a speed, not a velocity, a speed. So don't put in plus and minuses as if you think it knows what you mean by plus and minus. It's always going to ask how far how fast? What is the size of the acceleration? Not acceleration, but what is the size of the acceleration? It's always going to try to ask you in such a way that it doesn't necessarily assume that you mean that you are on a common basis in terms of what you mean by positive, right? And what you mean by negative. That's really important to understand. There's no universal plus or minus. It's just what you choose to use, especially in a problem like this where it's not imposed upon you. Occasionally there will be problems where it says, take the plus direction to be that way or this way, and then answer according to what it said. But that is more rare. Most of the time it asks you the thing in such a way that it doesn't impose sign on you. It gives you the question that way, and then also expects the answer that way. So make sure you understand that. So for WebAssign, it often asks for just sizes of things. All right? So don't put in the negative. It's not to say you shouldn't solve it with that, but then chop the sign at the end because it's not asking you for the velocity, it's asking you for the speed. Okay? Okay, so that's a couple different asides here, but let's knock off the rest of the problem. Let's do part B. Let me clear a little space for that. For part B, I want to put it below part A so I can show you. It's really just the same idea. I still have these same three things, right? Now the only difference is I'm being asked for the time to stop, right? I don't care about the displacement. Now you might say, didn't you just find it? Isn't it plus 5 meters? Yes. Well, let's say I felt like doing part B first, and I didn't know the answer to part A yet. That's a common misconception here, is that students think that the parts are way more intertwined than they really are. You can do this problem with part B first, using the same givens. You don't have to use your answer for part A. That's good on a practical level, because if you mess up part A, you don't want it to automatically mess up your part B, right? You can do these two parts in either order. Here, instead, which equation would I use? The first one, right? Because it's missing the displacement, and now you're working around that. Again, yes, you just found it, but let's pretend that maybe you're worried you got it wrong. If you're worried about progressive round-off error, let's try to just start from the same givens. So what does that look like? Let's copy it down. Here's the equation. On exams especially, I always appreciate when grading it that you write down what equation you're using before you proceed to plug in a bunch of stuff and have to figure out what it is. Okay? I'm looking for the time, so I solve for the time in this equation, and then I'm going to take advantage of the fact that plugging in units is just kind of a big waste of time, so let me just plug in 0 minus positive 5 over negative 2.5. I divide those, I get 2. I throw on, it's a time, 2 seconds. What's the time to stop? 2 seconds. Just like that. Which, by the way, you can't always do it in your head, but in this case you can, because look at this, right? What's the definition of acceleration? This is going to remove 2.5 meters per second every second. So after the first second, it's taken away 2.5. After the second second, it's taken the rest away. So it took 2 seconds. You can't always do it in your head if it's not a whole number of seconds like this, but this is very similar to the examples I was discussing before, right? So you take away 2.5 meters per second every second, you'll chew that up in exactly 2 seconds. And that's what I would put in the WebAssign because it is literally asking me for the stoppage time. Okay, are there any questions on that example? Okay, so this problem involves a car, and of course, you probably didn't blink an eye when I said it had this acceleration, and the acceleration was constant, because that's all a function of how you decide to brake, right? It's conceivable that you press the brake in such a way as to apply a constant acceleration. You can do problems like this where you have happen to have a constant acceleration, but the next thing I want to do, as I've already hinted at previously, is grab something from nature where we can rely on a constant acceleration. So let's do that. So let's talk about gravity. I already hinted that that's such an example of a constant acceleration, so let's get into that. So how does gravity work? All objects, regardless of mass or shape, are given a constant acceleration by gravity What are the properties of that? Well, and it's an acceleration, it's a vector, so it has both a size and a direction. To most generically talk about the direction, I'm going to say it's downward, because downward is something we understand in the real world. Downward could be notated as negative. It could be notated as positive if you wanted to. And later on in the course, we'll choose the positive axis as being like this. So then gravity being downward is not plus or minus. It's like this. So I'm trying to generically describe it without sign. Okay? Downward is downward regardless of what axis choice you want to make. The size of it is 9.8 meters per second squared. This occurs so often we give a label to that size. We call it lowercase g. Now, right off the bat, I should mention that this is not always true, but it is true if a couple things are the case. You're near the surface of Earth. And I am going to count those as two things, right? Because it's really two things. I can't be near the surface of Mars. I can't be far from the surface of Earth, right? I have to be near the surface of the planet we live on. All right? Earth, check. We are on Earth. Near the surface. How near the surface do you need to be? So let me give you a little bit of a scale drawing. Let's say this is the Earth, okay? Here is you at sea level. Here is the top of Mount Everest. Here is you in the highest airplane flying. Here is you at the bottom of Death Valley or something like that. The point I'm trying to make is that you might think that that is a significant change, but relative to the scale of the Earth, it's nothing. Okay? So when we say near the surface of Earth, we actually mean everywhere you will ever go in your entire lifetime, except maybe if space tourism takes off. Okay? So this encompasses all everyday situations that are conceivable. All everyday situations. So you might even wonder why we would bring up these caveats. Why wouldn't we just say this is always true? Well, we will go up into space. We will go to the surface of the moon and Mars. We will go far enough up above the Earth. The thing about physics is we don't have to restrict ourselves to where we actually can go. Okay? So it's my claim that in all everyday situations, gravity is given a constant acceleration. So what that means is that if I drop two objects from rest, I'm claiming they accelerate exactly the same, and so if they're trying to race each other to the ground, let's say, one should not have any advantage over the other, and they should land at the same time. Well, you obviously know that that's not true, okay? If I drop a bowling ball and I drop a feather, they don't hit the ground at the same time. The bowling ball goes clunk, and the feather goes like this, right? And lands much later. That has nothing to do with gravity, okay? Gravity, if it were up to gravity alone, they would hit the ground at the same time. The problem is that when you notice objects falling, it's not just gravity that's acting on them. Also air resistance. There's also air resistance. So what you actually observe, objects flying around, is actually the combination of gravity and air resistance. And air resistance is what treats those things differently. Okay? Air resistance can be significant or even dominant influence on something like a feather. Maybe you've noticed like a plastic bag blowing around and it's going up, rising into the sky. That's obviously not gravity, right? So air resistance can be significant, okay? So, it is my claim that if you could take air resistance out of the equation, or take it out of the situation. Now, it's hard because we don't normally think that we live in the, we're bottom dwellers on an ocean of air, right? And where we live. Air to us is basically invisible, and it's hard, it's easy to forget it, okay? But air resistance can be a significant factor, especially when something's moving fast through the air. All you have to do is stick your hand out a car window and you notice air resistance is significant. Okay? So, it is my claim that if we could take air resistance out of the situation, we would be able to see this. Now, you don't have to take my word for it. At the beginning of next lecture, I'm actually going to bring in a vacuum chamber where I will get to show you gravity naked without air resistance mucking it all up. Okay? So then we'll get to see how egalitarian gravity really is, how it really makes everything accelerate exactly the same. It's air resistance that mucks things up and makes it look different. So for our purposes, we're going to have to restrict our projectiles a little bit. We're going to have to go with baseballs and rocks and things like that, but no plastic bags or feathers, which have air resistance being a significant influence. So what we're going to basically do is we're going to pretend that air resistance is a negligible scenario because we're going to use relatively large aerodynamic objects where gravity, if not the only influence, is the dominant influence. Okay? So it's not that air resistance isn't there for bigger objects, but gravity plays a larger or dominant role in how they behave, and so what we can do is pretend that this is reasonably accurate even for them, even though these objects are not in a vacuum. Okay, so let's take a look at how we might encode all this stuff into a problem. Now, we could set the x direction as being vertical, but at some point we gotta acknowledge that we have to use something besides x. So for axes that are vertical, let's use y. So if I choose plus y to be upward, then of course anything that is upward is plus and anything that is downward is minus. So I guess I should also write down, I might want to write my variables like this. So I change my x's to y. So I have my 5 variables. Now they're y variables instead of x. Okay? So in this case, downward is this way. So my acceleration would be plus or minus? Minus. According to that choice, downward is minus. What's the amount? 9.8 meters per second squared. There's the direction. There's the size. As we will write it later, we will write it oftentimes as minus g as well. And here I want you to point out that the negative is not in the g, so we need to put it in the front. Okay? So g itself is not negative. G itself is just the size, and we wouldn't want the negative in there because that is forcing upon us a sign choice we may not always want to make. For example, what if we decide to choose downward to be plus. That's something that you occasionally might want to do. In fact, you will do it in your lab this week. So that means that anything that points downward is plus, whereas anything that points upward is minus. Well, gravity still acts downward, doesn't it? So my acceleration is like this. Is that plus or minus now? That's plus now. Plus 9.8 meters per second squared. The plus is the direction which I've associated, and the size, of course, never changes. And now, if we wanted to write that, we'd write it as plus g, right? So now, it would be horrible if there was a minus sign hiding inside the g, because we don't want it, right? So that's what we're going to do, is we're going to start applying this constant acceleration in the same strategy we were doing before. Now remember, there were 3 variables we needed, a minimum of 3. Well, we just got one of them permanently. So we only need 2. So we need 2 things. We already have the acceleration. We can be asked for a 4th. Don't know, don't care about a 5th. Okay? So this is a perfect just situation from nature that we can just grab and use with our toolkit. Okay? Now, why this is true is we're going to come back to later. We're basically grabbing it a little bit prematurely. We don't really understand anything about why this is true. You'll measure that it is true, by the way. Your lab will be to measure this g value. You will watch a plummeting object and figure out what is the g value. Okay? You don't have to take my word for it. You will measure that it is true. Why is it true? Worry about it later. Homework 6, in fact. But for right now, we're kind of grabbing it a little early because it's a perfect example of constant acceleration to use our equations with. So we'll do some examples of that next time.